How a $10 color sensor can estimate smoke particle size. Okay, so this little chip right here, it's smaller than your fingernail. Just watch smoke pass in front of it and told me two things most sensors can't tell you. Roughly how big the smoke particles are and roughly how much smoke is actually in the air. No lasers, no lab equipment, just four numbers it already had. Let's break down how it actually works. I'm explaining it like I am to a 5-year-old. Then I'll show you the real math. Here's the setup. I've got a little LED shining across a chamber, and on the other side, a sensor watching how much of that light makes it through. When smoke or fog drifts through the light beam, less light gets through. Simple enough, that's basically every smoke detector ever made. But here's the question a normal smoke detector can't answer. Is that dimming caused by a little bit of big stuff or a lot of tiny stuff? Because both of those can block the same amount of light. One transmission number alone can't tell them apart. You need another clue. Here's the trick. It's the same reason the sky is blue. Really tiny particles, way smaller than the wavelength of light, are bullies to short wavelengths. They scatter and soak up the blue light way more than the red light. That's literally why the sky looks blue. Tiny air molecules bouncing blue light around way more than red. And that's why the sunset looks red. The sunlight is traveling through more atmosphere, so even more of that blue gets scattered away. And mostly red survives the trip to your eyes. Now, the big particles don't play favorites. A fog droplet or a chunk of dust blocks blue light and red light almost equally. It doesn't care about color. It just gets in the way. So there's the If you shine light through smoke and check two different colors, and the blue one drops a lot more than a color like green, yellow, or red, that's a fingerprint. It tells you the stuff in the air is small. If both colors drop about the same amount, the stuff is bigger. You're not measuring size directly, you're measuring a color imbalance, and that imbalance is a proxy for size. This is how the actual chip comes in. It's called an OPT4048, and it doesn't just measure how much light. It has 4 channels that each care about different color bands. Z is tuned to care most about around 450 nanometers. That's blue. Y cares about 550 nanometers. That's green, right where our eyes are the most sensitive. X is weirder. 2-hump response. Think of it as a bonus clue. W is a wideband channel. It just grabs a broad slice of everything like regular light sensor would. So instead of one number, how dim it is, I get 4 numbers, each with a different color bias. And remember the sunset trick? Z blue, Y green are exactly the pair I need to catch that color imbalance. Here's the actual recipe, no scary math required. First, I note down the Z and the Y reading on a clear day. That's my baseline, my nothing's in the way number. My light beams are extremely stable, no flicker, no color changes. Whenever a new reading comes in, I check how much dimmer Z got compared to its baseline and how much dimmer Y got compared to its baseline. Then I compare those two dimming amounts. If blue Z dimmed a lot more than green Y, small particles. If they dimmed about the same, bigger particles. That's actually a name for this number in atmospheric science. It's called the angstrom exponent. Scientists have been using this exact blue versus green trick to study wildfire smoke, volcanic ash from satellites for decades. I'm just doing it on a $10 sensor sitting in my instrument instead of a spacecraft. Here's a real footage from a test. I lit a kerosene lantern near the sensor. Watch the wavelength reading shift as smoke drifts through. That shift is blue versus green imbalance showing up in real time. Once I know roughly how big the particles are, figuring out how many is just accounting. I know how much light got blocked overall. I know roughly how much light one particle that size would block. Divide one by the other, and I get a head count, particles per cubic centimeter of air. From there, it's just geometry. If I know the size and the count, I know the total volume of stuff, and if I assume a density for soot, I get an actual weight, micrograms of smoke per cubic meter of air. Same unit you'd see on an air quality report. That's the spike right there. I lit glycol fog and pushed the estimate smoke concentration up around 2,000 micrograms per cubic meter. So that's the whole trick. 4 color channels, a baseline, a ratio, and some 1940s era physics for how tiny spheres scatter light, and suddenly a sensor that only sees color can tell you something about particle size and how much stuff is actually in the air. It's not a lab-grade particle counter. It's got limits. I told you about the blind spot on the small end, and it turns out there's one on the large end too. Past a certain size, the physics I'm using breaks down, and it'll confidently hand you a number that's just wrong, not just imprecise. It also assumes you know what the smoke is made of, but for the cost of a sensor smaller than a fingernail, that's a pretty wild amount of information to pull out of 4 brightness numbers. Smokeless Chimney at smokelesschimney.com. Find us on Reddit, Facebook, and Blue Sky, as well as YouTube.